All right, so this is part 3 of the Kinetics series. Today we're going to be talking about reaction orders from graphs and like the half-life and integrated rate laws. So here is a review question from the last couple of weeks. The question reads, the following diagram represents mixtures of nitrogen monoxide gas and oxygen gas. These two substances react as follows. It has been determined experimentally that the rate is second order in nitrogen monoxide and first order in oxygen. Based on this fact, which of the following mixtures will have the fastest initial rate? I encourage you to take a pause the video here and try to figure out the question. So the answer here is 2. And if you remember from the lecture on reaction orders, the order of the reaction in relation to one of the reactants shows us how it will affect it, how increasing or decreasing the concentrations of one of the reactions will change the rate of the reaction. And then obviously for second order, it quadruples it, but for first order, it just doubles it if you increase it by twofold. Yeah, the answer here is number 2. And the reasoning behind it is, of course, that there is a higher concentration of nitrogen monoxide than oxygen. And that's necessary because in second order reactions, you actually have it, the reaction quadruples with an increase in nitrogen monoxide, but only doubles with an increase in the concentration of oxygen, because if you remember back to our lecture on reaction orders. Just as a little bit of review, the general form of a rate law is rate is equal to K times the concentration of reactant A to the power of M times the concentration of reactant B to the concentration of N. And then for the reaction shown on the slide here, M and N are reaction orders with respect to A and B, and then orders represent how rate is affected by change in reactant concentration, which is the theory behind what we used in the question on the previous slide here. Overall reaction order is M plus N, and any rate law must be determined experimentally. Rate orders are usually 0, 1, or 2. However, there are fractional and negative reaction orders as well. And then a quick thing about the Arrhenius equation. I really should have put this in the first presentation, but it shows the effect of temperature on K, which is why temperature affects the rate of a reaction. You can see the Arrhenius equation here, where K is the rate constant that you see at the beginning of the second half of the rate law, as you can see at the very top here. Where A is the pre-exponential factor, and then R is the universal gas constant. That's the one with either joules or with kilopascals, which again is equated, and then where T is the temperature in Kelvin. You also have to have activation energy for this equation, and you are occasionally asked to find activation energy from K, given this equation. I have seen it on the chemistry Olympiad exams. I have never seen this on the AP chemistry exams, and you will never be asked for it on there. If by chance that they do ask you, they will provide the equation for you because it is not on the official reference sheet. I do remember seeing this on one of Ms. Diardiva's exams, though, so it might be good to memorize it just in case. All right, so now we're going to get into integrated rate laws. And integrated rate laws basically allow you to find the concentration of A at a given period of time, given K and the initial concentration of A. The reactions, or the equations, sorry, are on the slide up here, and they can be found in the bottom left-hand corner of your reference sheet. So when you're finding integrated rate laws, this actually requires a little bit of calculus, so hooray, friends of calculus. If you think about the rate law, rate is the first derivative, so a lot like v of t in calculus. And then to get the concentration from rate, you need to integrate the equation. So it would be equated to getting x of t in AB. So to get the concentration of the rate, you rearrange the equation. Don't ask me how they came up with this. Some genius people did this, so we don't have to. And just as a note, you don't actually need to know how to do any of this for the exam. It's just good information to know, and it helps you understand where a lot of this comes from. And then you integrate the thing, and then you eventually end up with these 3 equations. Now, all you need to know how to do for Chem Olympiad and for the AP Chemistry exam is just how to use each of these. Well, firstly, which order each of these goes to, and then all you need to do is you need to find the order of the reaction, and then just plug everything in to find whatever you need, whether that be time given the two concentrations, the initial and so at some given time, or most likely you're going to be asked to find the concentration at a given time, given the time obviously and the initial concentration, and of course K. It's really easy. All you need to do is just plug in numbers. Pretty sure you guys all know how to do that, so we're going to just move on. And then now, so we're going to move into finding from graphs, or finding the rate law from, the order of the reaction from graphs, based on what function of the concentration of A creates a linear graph. It sounds a little complicated, but it's actually not that difficult. For zero order reactions, when you graph the concentration of A versus T, you're going to get a line with a slope of negative K. And in first order, you're going to have, when you graph the natural logarithm of the concentration of A versus time, that's going to be linear with a slope of negative K. And then for second order, you're going to have the graph of 1 over the concentration of A versus time is linear with a slope of K. Just as a note, it is not negative K. Just keep that in mind because it did throw me off when I first saw it. And then now you can actually see where this sort of comes from. In the integrated rate laws, you can see that first order has natural logarithm, second order has 1 over the concentration, and then zero order has nothing attached to it. So you can kind of equate those to what linearizes their graphs. This is a sample multiple choice question. It should give you a pretty good idea of what the type of question you'll see on the exams. Typically, you either get something like this, which states which of the following graphs may have been created using data gathered from the above reaction. So you can see that it's a second order reaction, and from what we know from the previous slide, that a second order reaction is linearized with a positive slope when you graph the 1 over the concentration of A versus T. You can figure out that the answer here is D. The other thing that you're occasionally asked to do is you'll be given a graph or a set of 3 graphs most often, where you have the graph of just the concentration of A versus time, the natural logarithm A versus time, and then the 1 over A versus time, and then you're going to be asked from there just to find the reaction or the rate order. You're never asked to do this with multiple reactants. So, for example, like having concentration of A times concentration of B, you're never really asked to do that. Yeah, just know that if that is what you are asked to do, you are going to be given them individually with the concentration of A and then the linearization of the concentration of B. They're going to be separate. Right, so the next thing we're going to go into is T1 half, or half-life, and you only need to know this for first-order reactions. So for first-order reactions and first-order reactions only, the half-life stays consistent throughout the course of the reaction. So the half-life of the reactants, half of the reactants disappear at some given time interval. You can see the graph in there, and here is a sample problem to kind of show you how it works. Usually you're going to be given this table, and then you can see here, you're just finding what the type of, what the order of the reaction is given this data. And you can see at every hour, you decrease the concentration of the reactants by half, by exactly half. So from that data, you can tell that this is a first order reaction. You cannot get any information about zero or second order or any other order. So if something like this is given and there's not like a consistent time, like a consistent time interval where half of the reactants disappear, your assumption there should be that you don't have enough information to figure out what the reaction order is. Yeah, and then the only other thing that you're occasionally asked to do is find the half-life, and the steps are really simple, actually. You just find, firstly you have to make sure that the reaction is first order, because if not, it will not have a consistent half-life, so you can't use this at all whatsoever. And then if there's a table, you're going to find where the concentration of A decreases to half of its original value, and then you can, you can find the time interval there. That's probably not that hard. I'm sure you guys have done that before. And then if you're just given K, or if you already found K, you can use this equation. T1 half is equal to natural logarithm of 2 over K. And then if you are doing the multiple choice, you will need to use the approximation 0.693. And you will just be doing, just plug it into this equation. That's it. And yeah, that's about it for this. There's really not that much. That just about wraps it up for this week's presentation. Next week, I will be going over the reaction mechanisms, the famed reaction mechanisms. This is where you get the multiple steps in the reaction. So look out for that, and have a nice day.